Hello, everybody. Welcome to this week's PMA colloquium. It's a pleasure to introduce Vladan Vuletić, and I'm a little bit sorry that we couldn't host him directly at Caltech. We had him scheduled in the spring, and then COVID came in. So Vladan is a pioneer, I would say, in AMO physics, developing various different techniques that are used all over the place now, and keeps on pioneering new things. And he will tell us about recent measurements for dark matter searches in his lab. Vladan did his PhD at the LMU Munich with Ted Hensch, and then stayed on there for a little bit, for a very short postdoc, before he moved to Stanford for a postdoc with Steve Chu. And then Stanford seemed to have liked him so much that they kept him as an assistant professor. And after a few years, he moved to MIT, where he became first an assistant professor and eventually a full professor, and he has been there since. Vladan has gotten a range of prizes from starting with Sloan fellowships. He's a fellow of the American Physical Society and so on. I don't want to list all of them, but he's widely recognized for his contributions in AMO physics. And with this, I will give over to Vladan. I should say that Vladan mentioned he would like it if there's questions during the talk, and I think this would make it a little bit more lively. So if you're, have some questions you would like to ask, maybe just try to raise your hand or type it into the Q&A box, and then I'll briefly interrupt Vladan. Vladan also has a short break in the very middle of the talk, and where we would wait for a second for questions to be asked. Okay, with this, I would hand over to Vladan to give the talk.
Thank you very much, Manuel, for the kind introduction. I would like to tell you about search for dark matter with atomic precision spectroscopy, although more accurately, maybe we should call it a search for physics beyond the standard model with atomic physics spectroscopy, atomic precision spectroscopy, because even if we were to discover a new particle from the way we do it, we wouldn't really be sure if that is the constituent, the dominant constituent of dark matter. This work was performed at MIT, but in collaboration with a number of people, including Won Ho Jae from the Seoul National University in South Korea, and calculations done by Julian Berengut and his co-worker Amy Geddes in Australia. So what I would like to tell you about is, just briefly remind you that there's much cosmological evidence that there is dark matter, or at least some physics that we don't understand. And then introduce you to the principle of our method, which goes back to a seminal proposal just 2 years ago by some theorists. And it's basically a search for a fifth force through the tools of precision spectroscopy and trapped and laser-cooled atoms. I would like then to introduce you to some results, isotope shift measurements on trapped terbium plus ions on 5 isotopes, where we observe a nonlinearity in a so-called king plot. I will explain what that is, which could potentially be a signature for a new boson, but also can reveal previously unseen or not precisely measured nuclear effects. And I will tell you a little bit about how we hope to distinguish those in the future. Then I would like to tell you a little bit about unpublished results on another, even weaker transition that is has a higher sensitivity, it turns out, to new particles and to nuclear effects within the standard model. And then finally, to give you an outlook of where we have hoped to go within the next couple of years or so. So there's hits for physics beyond the standard model, especially in the form of dark matter, abound in astrophysical and cosmological observations and effects. These are gravitational effects of various kinds that simply indicate that there's a larger mass than is observed in the stars. This includes gravitational lensing effects, where a galaxy bends the light from galaxies behind it. It includes rotation curves of galaxies that we really cannot understand the speed, how the velocity is a function of distance from the radius from the center of the galaxy, that we cannot really understand unless there's more mass in the galaxy than is visible. It includes collisions of galaxies that again indicate that there's more mass in the galaxies than the stars. The motion of galaxies within galaxy clusters, and also calculations to try to model the creation of galaxies that work much better if some dark matter is included. This is, for instance, an example of gravitational lensing taken by the Hubble telescope, where the galaxies in the background, their light is bent by galaxies in the foreground, which seems to indicate that there's more mass in the foreground than we see. This is another example, maybe the most prominent one, of dark matter, which is the so-called bullet cluster, where two colliding clusters of galaxies are causing gravitational lensing. And from the gravitational lensing, it looks like that the center of mass of these galaxies the center of mass location is different from the location of the center of mass of the stars. So there's a lot of evidence that thinks that there is some kind of dark matter, although nobody really knows the nature or origin. And other explanations, I should point out, are still possible. Other explanations include, instead of including more mass, one could change the laws of gravitation. One could try to modify general relativity or gravity in some other form. There are also proposals that dark matter might consist of miniature black holes and other wide open field. But if the dark matter is in the form of baryons, then what we do know is that it must interact weakly with standard matter and radiation to have avoided direct detection so far. We are hoping that it does not only interact gravitationally, and there are some indications that it would be hard to make models where dark matter interacts only gravitational and through no other force. So people have proposed, that dark matter consists of subatomic particles of unknown mass, and it's really unknown. Many orders of magnitudes are open, from micro electron volts, where you should think of dark matter particles more like waves. There are so many of them; they have little mass, to very heavy particles. And one really does not know. There are some favored models by different theorists and so on, but really it is not known. Basically, it's not really known where to look, and that's why people are looking in various mass ranges and for various particles. You might think that this is completely a search in the dark. One thing that's maybe a little bit encouraging is that some theoretical models argue that instead of having just one extra particle that is not in the standard model, it's maybe more likely that there's a whole family of dark matter particles, just like we have for the standard model particles. And so this would, of course, increase the detection probability, because there could be particles with different masses that exist. So in terms of searches, as I said, there are many ongoing searches for weakly interacting massive particles. Were a favorite for quite a while, so-called WIMPs, axions, dark photons that couple weakly to ordinary matter, but none of these has really provided any conclusive evidence so far. The searches can be divided up into two kinds of searches. So direct searches with particle physics methods, where one is looking for the trace of a particle in a detector, or a scattering event where particles are scattered of an unknown or unseen particle. But they are recently, because other methods have gained prominence, in particular methods that use the high precision, that leverage the high precision available, for instance, in atomic physics and some other areas, to look for indirect evidence of dark matter. So basically to use precision experiments at the low energy scale in atomic physics, the electron volt scale, to still have, because of the extraordinary precision, sensitivity up to tens or hundreds of mega electron volts, for instance, to have sensitivity at high energies. Another prominent example of this is, for instance, the search for a permanent electric dipole moment of the electron. And so the method that I will tell you about is of this indirect kind. We try to do precision spectroscopy at low energies in atomic spectra, and try to detect virtual new particles via the fifth force they would create in atoms. So I would like to stress here, we are not looking for particles that come from outer space and hit our experimental apparatus. Rather, we are looking for the virtual exchange of a hypothetical new particle that would lead to a new type of Yukawa type force. And as I said before, due to the high precision of spectroscopic measurements, we can be sensitive to high energy effects, because we measure transitions with high optical transitions with high fraction precision. So the principle of our method is simply the following. Imagine that there's some new particle, some new boson called phi in this picture, and imagine that this new boson has some sort of coupling to both the electron and the neutron. Then what can happen is in a Feynman diagram is that, say, a virtual particle is emitted by a neutron, this new boson, and absorbed by the electron. And this virtual exchange of this new boson between neutron and electron would create a Yukawa type potential that has 1 over r potential and then a cutoff, an exponential cutoff at a length scale that is set by the constant wavelength of this new boson. And so because we are looking in atoms, our natural length scale is somewhere between the size of the nucleus and then the size of the atom or beyond that. So we are sensitive in mass units for a mass range of about 100 of electron volts to 100 of MeV. Yes, I can see there's a question.
Mark, go ahead.
He's muted.
Yeah, I'm not sure if I can.
Can you hear me now?
Yeah.
Yes.
Sorry. Yeah, my skills here are very limited. So this potential that you're writing, that's just a proportional to, not an equals, right? There's
right. Yes.
Yeah. Okay.
So, yes. Yeah. There's a coupling factor here in front in some dimensions. Thank you. I should correct this. Yes, it's just proportional. Okay. So there's a coupling strength that you're sensitive to. Thank you for pointing that out. Mm-hmm. Yes, so it's just proportional to. So if this new boson also couples to protons, that would be fine. We would just not be sensitive to it because what we're doing is we're comparing this new Yukawa type potential in different isotopes of the same element. And so we are really sensitive only to changes in the neutron number rather than in the proton number. So maybe one way to visualize this is the following. If you have a Coulomb potential here, 1 over r Coulomb potential that's somewhere cut off by the nucleus, then you have the atomic energy levels labeled G and E in this potential. If you have now an extra term here, and here I have not omitted the coupling, so I have an extra potential as pointed out proportional to with some coupling YE to the electron and some coupling YN to the neutron. So we are only sensitive to the product of the two. And then it's proportional to the neutron number inside the nucleus, this extra term here. That would slightly offset this Coulomb potential slightly, ever so slightly shift the energy levels in the atom. And then we would measure different energy levels. Now, unfortunately, we cannot directly compare experiment to theory because in all atoms other than hydrogen and maybe helium, the atomic level structure is too complicated to calculate accurately. We can measure transitions with 12, 15, 18 digits in principle in atoms with many electrons, but we can not calculate them anywhere close to directly compare experiment to theoretical prediction. So this is where the seminal idea comes in by Yotam Sorek, Gilad Perez, Roy Ozeri, and C. Delaunay, and then later worked out in this PRL. So it's only idea 2 or 3 years old. And the idea is that instead of comparing experiments to theory, what you can do is you can measure this transition in different isotopes, and if you plot things in a particular way, you can sidestep the need to do calculations, and you can directly compare experiment to experiment if you want. And as I will show you, this idea works, but with certain caveats that have to do with the interaction and the size of the nucleus. So the basic idea is, instead of comparing experiment to theory, we just compare different isotopes to each other and try to draw inference about changes to the potential. Or somebody asked, I didn't catch why the coupling is only to the neutrons and not to the protons. No, the coupling can also, very good question. The coupling can also be to the protons. We just wouldn't see the difference because we're always measuring an atom, in a particular atom with the same number of protons, but just the neutron number is changing. So it could couple to protons. We're just not sensitive to that measurement. Thank you for the question. Okay, so how does this work? Well, if one measures so-called isotope shift. What is an isotope shift? It's a frequency difference between say an optical transition, in our case, in two isotopes. So I label this by nu alpha ji. So this is the difference in optical frequencies on a transition alpha, labeled alpha, between two isotopes that I label J and I. So here I have three subscripts. One is the kind of transition that I'm using, and then 2α for the two isotopes that I'm comparing. The Latin letters are for J and I are the isotopes. So it turns out that I can write this isotope shift to leading order in the following form. There's a term that is called the mass shift. It's basically the reduced mass difference of the two isotopes, labeled by mu gi. So think of this as just the reduced mass of the electron, because the nucleus has different mass. The reduced mass of the electron is a little bit different in the two isotopes. That's the so-called mass shift, and it has some prefactor. So it turns out that I can write this as a property of the nucleus, in this case, the mass of the nucleus, mass difference of the nucleus mu gi, and then a property of the electrons, in this case, the electron orbits. And then another effect that is large is the change in the size of the nucleus. So the Coulomb potential gets cut off by at the size of the nucleus. And so if the two nuclei J and I have different RMS radius, then there's a shift that comes simply from the fact the Coulomb potential stops earlier or later in the two isotopes. This one goes as the nuclear size difference, delta R squared, again with a pre-electronic factor that depends on the electron density near the origin. This is the nuclear size difference or field shift effect. It turns out that in light atoms, the mass shift dominates because the fractional change of the nuclear mass is the biggest, whereas in heavy elements, like we work in a terbium, the field shift dominates and is about an order of magnitude larger than the mass shift in our system. So these are the two dominant effects. The isotope shift is typically on the order of gigahertz, and 90% of that comes from this field shift. Now it turns out that when you combine the two transitions, as I will show you in a moment, when you measure not only on one transition, but actually on two transitions, then you can imagine that I can cancel this unknown delta R square term, and mu, the masses of the atoms, can be measured very accurately. So when I'm combining these two transitions, the first two terms will give a linear relationship. However, there are other effects, smaller by 7, 8 orders, 6, 7, 8 orders of magnitude. And an effect within the standard model, the leading order term, we believe, is the so-called second order field shift. So you can think of this as an expansion in the change of nuclear radius delta R squared. This is the linear term, the linear field shift in expansion. And then there's a much smaller term, which is the second order or quadratic field shift in this expansion. And again, it depends on the properties of the nucleus, delta R squared in this case, and then an electronic wave function factor that is in principle calculable. And then here I have added a hypothetical coupling to a new boson. This scales with the difference in neutron number between the two isotopes that I've labeled here AGI. So that's just the number, say between neighboring even isotopes, it would be 2. Then there's some new boson coupling, this dimensionless coupling of how strongly the new boson couples to the neutron and the electron, the product of the two. And finally, there's again an electron wave function here, which basically tells me how much does the energy level shift due to this Yukawa type potential. So there's a question I can see, David Hitlin.
David, please. Try to unmute you. I think you might be muted still.
Sorry. Ytterbium has a permanent quadrupole deformation, which differs from isotope to isotope.
That's a very good, you're kind of stealing some of my thunder. So we believe that the next order shift that has a comparable magnitude to the second order field shift is the quadrupolar deformation. And I will show you unpublished data that seems strong to point in that direction. Yeah, I would be, maybe we can discuss this later. That would be very, very interesting to discuss. Yes, there's a second term, which is the quadrupole deformation of the nucleus. I completely agree. Thank you for that point. To measure this linearity now, when we plot things on a line, we are measuring isotope shifts, and to test whether some behavior is linear or not, we need at least 3 data points. So we need at least 4 different isotopes. It turns out that we have, or at least it's much easier to use spinless isotopes, isotopes without a nuclear spin, because otherwise the hyperfine interaction complicates things. So what we have at our disposal, it turns out in ytterbium are 5 stable isotopes of 0 nuclear spin that we can use to test this linearity. And so this is now basically when you take 2 difference frequencies and say divide them by each other, then you can write the isotope shift on one transition normalized to the isotope shift at the other transition as a linear function of the original isotope shift with some prefactor that is related to the field shift and some prefactor that is related to the mass shift. So these 2 terms basically plotting the normalized isotope shift on one transition versus the normalized isotope shift on the other transition give you a linear behavior. And then in general, these nuclear shape effects like a quadratic field shift or possibly the quadrupole deformation or possibly any dark matter would likely contain nonlinear terms depending on their structure. So basically the idea is that these get shifted away from the line like so. How sensitive could you get with this? This shows you the calculated sensitivity from this proposal paper by Berengut et al. So what is shown on the horizontal axis is the mass of this hypothetical new boson in a range from 10 electron volt to 10 to the 8th, so 100 mega electron volt or so. What is shown on the vertical axis is in dimensions units, the product of the couplings to the electron and neutron. This is what we are sensitive to. And so it ranges down here to 10 to minus 17 is these natural units. This is normalized in such a way that the electromagnetic coupling would have unity strength. The coupling of the, to the electric charge would have unity strength on this axis. So the solid line is existing, previously existing data measurements on calcium plus at 100 kilohertz level from a few years ago, which you can see limit this at, at a certain strength. The blue shaded data or the blue shaded region is derived from G-2 electron, G-2 measurements on the electron by Jerry Gabrielse in combination with analysis of neutron scattering data by neutron scattering experiments, because you're sensitive here both to YE and YN. This is somewhat model dependent, but it's not completely model free, but it's some reasonable models. So the blue region would be the more or less excluded regions, at least in certain models. The orange, these measurements here on the left, dark orange, were excluded by fifth force, and these are much more sensitive than we can hope to be. So below 100 electron volts, we really don't have much to say. And then in this region between 100 electron volts and 10 to 100 MeV, the orange, the light orange data are data based on astrophysical observations. Supernova cooling sets certain limits. Again, these limits are somewhat model dependent because you have to assume that you know something about the mechanisms, the physical mechanisms in these stars and supernova and so on. So even if these are excluded, it would be actually nice to test them in a laboratory experiment. But then there are also white regions that are, for instance, also not excluded by accelerator data. And here in green is shown the prediction for ytterbium if a measurement of an optical transition at the 1 Hertz frequency, 1 Hertz uncertainty can be performed. And you can see that would start to get into this yet unexplored region in white and also into some of these astrophysical limits. To give you an idea where we are, the force range, basically we can convert this mass scale into via the Compton wavelength of the hypothetical particle into a length scale. So here where the blue line is roughly where the Yukawa potential range becomes smaller than the size of the atom. There we start to lose sensitivity, basically because the smaller the ranges, the less and less affects atomic levels. And then over here on the red side is where the force range becomes smaller than the size of the nucleus. And there we really have very little sensitivity because it's hard to distinguish, any Yukawa potential of that short range from a direct contact interaction term between electrons and the nucleus. So the most interesting region is kind of here between the 100 eV and then region over there. I would like to also point out this. This is the so-called atom key anomaly experiment, a nuclear physics experiment done in Hungary, where they observed that when they created excited beryllium nuclei by bombarding lithium with protons and creating beryllium in an excited state, they observed that it decayed sometimes into electron-positron pairs, and these electron-positron pairs were observed with a coincidence angle of 140 degrees at the 7 sigma level or so. And because this was observed only for a certain transition at above 17 MeV, but not below 70 MeV for another transition, they can make some inference that if this were due to a new unknown particle, it would have a mass in the range or near 17 MeV. And there can also be some inference about the coupling can be made. These experiments have recently been repeated in the same apparatus for excited helium atoms, helium nuclei, which decay with an energy of 21 MeV. When I talk to nuclear physicists, experimentalists, there's some hesitancy to accept these results, but they will be remeasured. One of the problems might be that they use the same equipment for both experiment, and that they might, you have to calibrate, as far as I understand, these angles very accurately. But basically, this is the bump, this excess that they see in coincident events for helium, in this case, around 110 degrees or so. So the story is basically that if we can measure at 1 Hertz, we could potentially exclude this atomic nonlinearity. What is the cause of the dip in sensitivity? From Eric Hudson, you mean in these atomic physics curves? If you're meaning these kind of anti-resonances, if you want. I'm not sure, Eric, do you mean the anti-resonances here, or do you mean the loss of sensitivity at high masses? Can you maybe unmute Eric Hudson?
To find him, I would suspect he's asking for these cusps.
Okay,
I have the same question actually.
Mm-hmm.
Yeah. Okay. So yes, the cusps.
So the cusps really arise from the fact that if you have a certain Yukawa potential for certain wave functions, or for certain size of the potential, it can affect both the ground state and the excited state in exactly the same way. Right? You can imagine you have a ground state extent, you have an excited state extent of the wave function, and then you have this Yukawa potential. And if it has a particular range, then the ground and the excited state move together. So basically, you wouldn't be sensitive to any shift. You wouldn't be sensitive to this mass of the Yukawa potential. However, if you now change your transition and measure instead a different transition, you would get a cusp in a different location. And so in that way, you could, remove these regions of low sensitivity. Does that answer your question, Eric? Resonances. Mm-hmm. Okay, so I hope that makes sense. Basically, these are places where the Yukawa potential range is just such so that it moves both the ground and the excited state together, and therefore we are not sensitive to it. And by choosing a different transition, you can have cusps in different locations. This was calculated for one particular transition. Thank you for the question. So this is our experimental. Actually, let me maybe, there were already a number of questions, but maybe this is a good place to pause and see if there are any other questions so far before I start talking about our experiment. Not, yeah, please continue to ask me during the talk, and maybe just. Okay, so this is our experiment. We use laser-cooled terbium ion, or a single laser-cooled terbium ion inside a vacuum chamber that we laser cool and then spectroscopically address. And a very simplified level structure of the terbium ion looks like this. Terbium is a single electron atom in the outer shell. So it has an atom in an S state, looks like hydrogen, so to speak. There's a strong S2P transition at 369 nanometers that we use for fluorescence detection. So that transition is also used to take this picture. So basically we illuminate the atom with a laser on this 369 nanometer transition, and it fluoresces as long as it's in the ground state. And then when we turn off this laser, we can try to drive with a probe laser one of these transitions. I will first talk about these two D levels, D3½ and D5². So what we can do is we can try to address an atom on an ion on this transition, excuse me, on this transition. And if the ion made this transition to the D state, which is long-lived, these D states live for several seconds or so, then basically the ion goes dark on us. Then when we turn on the fluorescence laser, the ion is not there. And then when we drive the system back by optically pumping the ion out of this D state, the ion reappears. So basically we can tell that whether the transition happened or not. This is called electron shelving, by just looking at whether the ion goes dark on our fluorescence transition or not. So the challenge is to make these lasers stable and narrowband enough and to address these narrow transitions. So the first data I will show you are about these 2D levels. Now what you're measuring really is a difference between 2D states. So if these electron wave functions were identical, and if this was a single particle wave function, these would be non-relativistically identical, we would have no sensitivity. However, because this is a relativistic many electron atom, actually these states have slightly different wave functions, and therefore we are sensitive to a change in the Yukawa potential, or to the Yukawa potential as affecting these two states differently. The atoms share the same S ground state, so we are really not sensitive to the Yukawa potential in the ground state. Okay, so there's a question, one ion or a cloud of many, and if many, do we have to count interaction? We do things with one ion for exactly this reason, to not to have to worry too much about interaction effects, etc. So what we do right now is we load one ion of one isotope, measure it for about 30 minutes, then replace the ion, measure this ion, single ion, and go back and forth. So you're right, with more ions, we could have, better signal to noise potentially, but also to account for more effects. So that's why right now we just do measurements with a single ion. Thank you for this question. Let's see, is there any other? Okay, good. So it's really a measurement with a single ion. So I'll show you measurement now on these, comparing these 2D transitions. So the way we do this for the experts, we do a so-called Ramsey sequence. This is basically the fluorescence as a function of the fluorescence over many, average fluorescence over many trials of the experiment as a function of the detuning of the probe laser. What one sees are these so-called Ramsey fringes, these periodic fringes as a function of frequency, and then we can fit them. And from the fit, we can extract the center frequency of the transition. And for the experts, again, we do this for two different magnetic sublevels and two different transitions that have opposite Zeeman detunings, opposite magnetic field detunings, and we average over those to get to linear order independent of the magnetic field in the system. And when we do the measurement and show one transition on one axis, the D3½ transition on one axis, the D5½ transition on the other axis, in this normalized frequency units, we see a beautiful line. This is the most accurate linear plot I have ever measured in my career so far. However, when we zoom in by a factor of about 1 million or so, so break this axis, and then there's a distance of 1 million, and then there's the second piece of the axis, etc., of the vertical axis and also the horizontal axis, then we see a slight deviation from this best linear fit. The deviation for each individual point is on the order of 1 kilohertz in frequency units. When you convert this to frequency units, we are about 1 kilohertz off. Our error bars on each individual point is about 300 hertz or so. And these error ellipses for these 3 points on the left come from our frequency uncertainty of the transition. When we combine all 4 data points, then the overall deviation from a linear fit, so we can say that data agree or do not agree with a linear fit at the level of 3.3 sigma, 3.3 standard deviations. This point here has a much larger error ellipse. This is because we measure between isotope pairs. So what the labels here are, 174 ytterbium directly compared to 176 ytterbium, 172 to 174. So we measure always pairs. And here we measure 168 relative to 170. And 168 is a fairly rare isotope, I think 0.1% or so natural abundancy. And so it turns out that the mass for this isotope had not been measured so accurately. Fortunately, the mass error is correlated. So basically, because these transitions are relatively similar, the mass error would affect in a similar way one transition as it would the other transitions. So So the error bar is almost parallel to the line and doesn't affect us very much. In the meantime, after publication of our results last couple of months or so, a new measurement has been made of this 168 mass, which agrees within 1 sigma with the old measurement, and also makes now the mass error smaller than our frequency errors at the current region. So we see this nonlinearity, or we have evidence at the 3.3 sigma level, and of course you can ask, is this originating from nuclear physics simply that is within the standard model? So fortunately, we can measure not only the magnitude of this nonlinearity, how much it deviates from a line, we can also measure the pattern because we have 4 points here. So we can just, with these 4 data points, 5 isotopes, we can look at the pattern. In particular, if you think about it for a moment, if you fit 4 points of a line and it doesn't fit perfectly, there are only 2 ways that the points can deviate from the line. There can be a zigzag nonlinearity where neighboring points lie on opposite sides of the line. So it's up, down, or down, up. Or there can be a curved nonlinearity where basically the first point and the last point lie on one side of the line, and then the other 2 points, the middle 2 points, lie on the other side of the line. And then you can assign kind of a sign to this zigzag nonlinearity depending on whether the first point is above or below. And you can also assign a sign to the curved nonlinearity. So basically we have a parameter space with 2 axes going from positive to negative that characterize how much zigzag nonlinearity there is. We label this zeta plus, and how much curved nonlinearity there is. So we can extract these 2 measures from our data in a unique way. And so we can plot now our nonlinearity, not only the magnitude, but the pattern, where we plot the zigzag amount, the zigzag contribution around the horizontal axis, and the curved nonlinearity along the vertical axis. And 0 means in this plot no nonlinearity. So if we observe the linear behavior, we would be at the origin. This is a 1 sigma standard deviation, our error ellipse, when we combine all these data points in this new way of plotting the graph. And the reason to do this is the following. Since we know what the second order field shifts, we know the functional dependence of the second order field shift, that it goes as delta r squared squared, and we can extract delta r squared squared from the linear field shift with very high accuracy. We can predict basically the line and along which any second order field shift effect must lie, and that is the green line in this plot. So if you don't know how much second order field shift there is, you don't know the electron wave functions very well, but you know the direction in which it will lie along this line very well. So any effect a second order field shift would have to lie on the green line, and in principle we can even calculate if we understand the electron wave function very well, we could predict where along this green line the point should lie. Now the new boson also has a known functional dependence, because we know that this coupling should be proportional to the neutron number in the atom, in the ion, and therefore the new boson we can predict has to lie along this blue line here. So any dark matter coupling would be along the blue line of the form that I've described. So we can see that at the current level of precision, we cannot really strongly distinguish between a pure second order field shift or potentially a new boson or some combination between the 2. We can plot things in a slightly different way if we like to kind of quantify what we have in the system, the trade-off between second order field shift and new bosons. So if I plot the second order field shift on the vertical axis in some experimental units that we can then convert into fundamental units, and the dark matter coupling again in experimental units and hertz on the horizontal axis, then our data are consistent with no dark matter coupling and a certain magnitude of second order field shift, or potentially with strong dark matter coupling and very little quadratic field shift, or something in between. So how can we do better? If, for instance, we improve the measurements and made this error ellipse smaller by a factor 10 or so, and say we were lying over here, then we would conclude that we have 2 effects contributing, that things cannot be explained by the second order field shift alone or by the dark matter alone. So put another way, if I in this kind of plot make a measurement over here, sorry, doesn't work my annotation, make a measurement over here, I can infer whether it's second order field shift alone or something else. So one can improve the measurement, and one can also potentially improve the calculations, because if we improve the electronic wave function calculations, then we can predict the quadratic field shift, and then that gives us an inference on how much on dark matter coupling there might be. So if we assume that we have no dominant quadratic field shift, that the quadratic field shift is very small, and take this value of the dark matter coupling and plot it now against the hypothetical mass of the new boson, in this range that we had before, then this would correspond to this shaded region. You can think of this as an upper bound of the coupling. Basically, this is the coupling if the quadratic field shift is much smaller than the dark matter coupling, and then we would get this value, but any contribution to the quadratic field shift would actually lower this value. So this should be thought more as a limit. Here I've presented two different calculations, one done by my student, Jun, who used one method, and because given the solid line, this is many body calculation done by Julian Berengut and co-workers. The two calculations don't quite agree on the position of these resonances, simply because they predict slightly different wave functions for the electrons, and that makes them large shift in the potential mass of the sensitivity curve for the new particle. I would also like to point out, so this was published earlier this year, in the same issue, a measurement with the lighter atom calcium plus by the Drusen group was published under this reference. They measured about 10 to 20 times higher frequency resolution. So we have an uncertainty of about 300 Hertz. They have an uncertainty of about 20 Hertz. However, their lighter calcium atom is about less sensitive by something like the same factor, maybe a slightly bigger factor, less sensitive than our experiment for the same precision measurement. And they observed no nonlinearity within their that deviation. So this probably means that we are seeing some nuclear effects in ytterbium that are much more pronounced in ytterbium than in the lighter calcium atom. So these are the published results. Now I would like to tell you about some newest results that we are still in the process of analyzing very well and evaluating. And here we add another transition. We now, besides these two D states, we measure this so-called Octupole transition at 467 nanometers. This transition is extremely, extremely weak. This is a very special state in the sense that there's an excitation to an F level, and there's no other ground state beneath it. So basically you're driving a transition from an L equals 0 state to an L equals 3 state. So 3 units of angular momentum. So this transition is very highly forbidden, and calculations indicate that if you placed an atom in this F state, the natural lifetime for decaying to the ground state would be probably 10 or 20 years. So it's an extremely weak transition. So to drive it, we need a lot of laser power, but we managed to find this transition. This transition had been found in one isotope before. We managed to find it in the other isotopes, and I identified and make isotope shifts on this transition as well. So now we are plotting the frequency shift on the F transition here, the 467 nanometer transition on the vertical line. We normalize it to the 436 shift to get the king plot, and then we have the normal mass shift here on the horizontal line for the other transition. Again, we see nice fit by eye if we kind of just look at the whole picture, but when we zoom in by a factor of almost 1 million again, we see that the residuals actually deviate quite strongly from linearity. So now these error bars are actually absolutely larger. We have zoomed in by a factor about 10 less. These error bars are about 1 kilohertz in frequency units, but the deviations are on the order of 10 kilohertz or so. So if we compare this to the 2D state comparison, we notice first, of course, that the effect was much smaller in units, in normal units, but also that basically the pattern is different, right? Here we observe the almost pure zigzag pattern on these 2D transitions. Now when we compare the F to the D transition, we observe a pattern that looks much more like a curved nonlinearity with some component of zigzag. But it's a large effect. The effect is now on the order of 10 sigma. And as I will show you in a moment, this indicates that we have actually not one, but two sources of nonlinearity in this problem. So again, in this, when we analyze the pattern in this plot where we do zeta plus and zeta minus, this is the old measurement, the 3½ d 5½ comparison. And when we go here, this is our new data point where we compare the F to the D states. So we see that it has a completely different location in this graph, and it's a very large nonlinearity. This is partly, even though we are not measuring more precisely, because this transition is, as I said, about 20 times more sensitive to both nuclear effects and the new boson, because basically electron wave functions between the D states are relatively similar, whereas the wave function between the electron wave functions between the D and the F states are much more different. So if we try to explain things with one effect, it would correspond, it would have to align like this. So if we had a single nonlinearity, it would have to have a certain pattern in this zeta plus zeta minus plane. It would lie on that line. This is the best line that we can fit. So at the kind of 3 sigma level, we can conclude, at the moment we'll do a better analysis in the future, that we are actually having not one effect contribute, but 2 effects contributing. So 2 sources of nonlinearity. If we try to explain this just with the quadratic field shift and dark matter, it doesn't make much sense. If you have these 2 effects, because they have to lie on these lines, you can think of the displacement from the origin as a vector sum along the dark matter line and the quadratic field shift line. So you could basically go, would have this amount of dark matter coupling and then this amount of quadratic field shift coupling. And this is not realistic because we can calculate the quadratic field shift coupling. And although we don't know exactly what it is, we have indications that it's 3 to 5 times smaller than the quadratic field shift coupling that we would need to explain it by dark matter alone. So the question is, what is it that causes this effect? And here already somebody pointed out that the quadrupole deformation of the nucleus is a possible nonlinearity, and that has been also pointed out by Victor Juba, Vladimir Flambaum, Victor Flambaum and collaborators in this paper. So we are currently in the what is this? The idea is that if the nucleus is elliptical, and it's different, different ellipsoid for 2 different nuclear isotopes I and J. Because we cannot, fix the nuclear axis in the direction, we are really averaging. You can think of this, we are averaging over all possible spatial orientations of the nucleus because we're in the ground state. So when we average over all these effects, we get an effective spherical potential, but that spherical potential has a, charge distribution which is different for the nuclear isotopes I and J. So it will lead to an effective change in the term delta R to the 4th. So of course the effective size of the nucleus, delta R squared, will also be affected. However, that will be reabsorbed into the linear field shift. And then there will be also an effect on the quadratic field shift that we're trying to evaluate right now, how large that is. But that will be kind of reabsorbed into the other quadratic field shift that we think already exists. But in addition to that, there will be a new term effectively in this expansion. So if I rewrite this formula for the King plot, so again, the normalized isotope shift on one transition versus the normalized isotope on the other shift on the other transitions. This is the linear dependence. Then there's the quadratic field shift that we already talked about, which is the change in the radius squared to the 2nd power squared. And then there's also this effective effect in delta R, change in delta R to the 4, which comes from the nuclear deformation. There could be a real deformation. That one we know that that effect was small, but we are now evaluating. It looks like the quadrupole deformation might be enough to make the term large enough to explain our data. So very preliminary, one can ask, what is known about the quadrupole nuclear deformation and in which direction in this zeta plus zeta minus plate should it really lie. We have talked to some nuclear theorists that can do ab initio calculations, although we would like to understand how accurate they are. But if I put their calculations, this is with Nazarevich and co-workers, if I put their calculation, then nuclear quadrupole deformation should show up along this red line, like so. And we are currently trying to evaluate the magnitude to just see whether this much of observed nonlinearity can really be explained by the nuclear quadrupole deformation. So where do we go in the future? We can make the measurements several orders of magnitude more precise, as I will show you in a moment. We can also measure more transitions. We can potentially measure, and that's maybe one of the most interesting directions, more isotopes, including unstable isotopes. What that means is that we get more data points, which means that we can characterize the nonlinearity pattern better. So with 5 isotopes, we have 2 different patterns, zeta plus and zeta minus. But if we have add a 6th isotope, then this plot becomes 3-dimensional and becomes a lot more restrictive on the possible effects. And finally, what we also plan to do in the near future, we have a neutral atom optical transition clock, and it is possible to make a king plot of neutral ytterbium versus the ytterbium ion. Such a plot would have much higher sensitivity because not only the excited state wave functions would be different, but also the ground state wave functions are very different for neutral ytterbium and for ytterbium plus. In terms of what precision can be achieved, we are currently at the level of a few hundred hertz. It's really limited by the fact that we try to do the simplest experiment possible, which is, we measure one isotope for half an hour, then we switch to another isotope, measure for half an hour, and in the meantime, our laser is always locked to an ultra-stable cavity. But that cavity drifts in time. And so, for instance, Roy Ozeri and his group have demonstrated precision instead of a few hundred hertz at the 10 millihertz level by co-trapping 2 ions at the same time, taking care of many possible systematic effects and interrogating them at the same time. The beauty of it is if you make either an entangled state or somehow filter out an entangled state, you can take out the laser noise. So you can basically make each atom a superposition of the ground and excited state, and you can directly observe the beat node between one isotope shift and the other isotope shift without being affected by any noise of the laser. And that's what allowed them to do this 10 millihertz resolution measurement. So in principle, one can shrink these error ellipses down by 3-4 orders of magnitude in the future with just methods that have already been demonstrated. So this brings me to the end of my talk. As I have already said, I think that we don't know whether we will discover dark matter, but in the effort to put a limit on dark matter, I think that we will be able to measure, quantify previously unobserved nuclear properties in ytterbium plus, and hopefully also, via this pattern method, separate the different effects, separate and quantify the different effects. This will require input from, both nuclear theory, ideally, because it would be nice, or nuclear experiment. If somebody could measure the quadrupole deformation of the ytterbium nucleus for different isotopes more precisely, or calculate it more precisely. It also requires input from atomic physics theory, because the more accurately we can calculate the electronic structure, wave functions, the more accurately we can predict how large a quadratic field shift effect and other nonlinearities, for instance, should be in this. So we look really forward to an interesting collaboration with different groups. Thank you very much for your attention.
Okay. Thank you, Vladan, for a really, really nice talk. Everyone, we have some time for a question. David is asking one, so let me try to give it to you. David,
yeah, it would seem to be advantageous to find a set of isotopes with smaller quadrupole deformation. There are a whole set of neodymium isotopes, even nuclei, which probably have DF levels not so different, but which have much smaller quadrupole moments.
I mean, this is exactly the kind of input that we need for the future. That's a very good suggestion. We have a few requirements, right? We need narrow optical transitions. We need enough stable isotopes, spinless isotopes. And we need to be able to laser cool them so that we can cool and trap them and measure this with this very high precision. So I believe that there are better isotopes for the future. For instance, for neodymium, I don't think anybody has laser cooled and trapped it. So one would need to figure out the transitions. One would need to figure out how many isotopes one needs. But it's a very interesting direction for the future, especially if we were to conclude in ytterbium that it looks like there's an unexplained effect that is not explained by nuclear physics. The best thing to do would be actually to try to verify it by measurements on a different isotope. Yeah, so I'm very grateful for any input that can point to the future. The situation was simply we had already an ytterbium ion experiment at our disposal. Otherwise, we wouldn't have been able to pull this off within a year and a half or so since the proposal came out. But if one wants to push this in the future, I think that I agree with you, there are better isotopes and atoms available. So there are other people.
Oh no, there was Jeff. Did I miss you? Oh no, wait a second. So allowed to talk. Jeff, I think you could just go ahead.
Okay, can you hear me?
Yes.
So my cherished belief is that every trap, when you get enough digits, shifts the levels, even magic wavelengths. So at the the 19th decimal place, magic wavelengths are not magic.
Mm-hmm.
But I don't know anything about how evil the magic is if I'm talking about the optical transitions as well as the structure of the nucleus itself. If you turned up the electric field in the trap large enough, and you're never exactly at the null, put it in the ground state, and what's the role of the trapping? Is it obvious that it's well below kilohertz shifts, or that it's part into the 15th, or what?
Yes, people have evaluated in the context of single ion clocks in ion traps. So there, I agree with you. At some level, there is an effect. However, down to 10 to the minus 16 or so, I'm pretty sure that there's no such, talking about 0.1 hertz, 0.01 hertz, there's no such effect. People have looked at this very carefully because, for instance, terbium is one of the ions, used for evaluating clock transition, and in particular, this F transition has been, promoted as a clock transitions, and people have looked very carefully at it. So before the trap comes in, a variety of other effects come in, the light shift while you're driving the Ramsey pulses, for instance, and so on. We are still quite far away from these effects. So kind of down to the 1 hertz level, we are pretty safe. Then we'll have to look more carefully. But just to give you an idea, this is now a kilohertz level shift. If we bring this down to a hertz level, we will shrink the error ellipse by a factor of 1,000. All right. At that point, you're almost not learning so much anymore unless your model becomes much better. So I think we are pretty safe for the medium future. Beyond that, I agree completely, Jeff. One has to evaluate these things very accurately, but one can do that. For instance, when one measures with 2 isotopes, or what Roy Ozeri did cleverly, is you measure them in this configuration, and in the opposite configuration, you switch back and forth. Since you're only looking at the frequency difference between the two, you can again cancel to some leading order any effects that the trap can have.
Jeff, is your question answered?
Yes, certainly. Thank you.
Thanks, Jeff. Okay, so no, we lost someone here. There was another question. Okay, but let me read one of the ones that came in the chat from Rishbach. At the beginning, you gave an equation for the shift in frequency of the electron emitted during the isotope transition. Could you quickly give the dimension of alpha?
So here alpha was just a label. So it's only labeling the transition. So transition is alpha and the transition is beta. So in the very first frequency shift, the units are just hertz. So in this original, in this original equation, the units of this are just hertz. These are all SI units. And then what you can do to make this linear, you can divide either by the reduced mass or by the transition frequency on the other transition. Either way, you get a linear relationship. So in this plot, for instance, this tilde beta is the shift in hertz on the beta transition, on the second transition, divided by the shift in hertz on the first transition. And then this here is the frequency shift on the first transition divided by the mass difference that has been precisely measured. I hope this answers your question. So it's just in normal units. Yeah, do you want? Mm-hmm.
Okay, I think we have one more question from David.
There's one in the chat more says, how much complications? That's a very interesting question that I would like to comment about. How much complication do 171 and 173 add? It is known that if you take isotopes of hyperfine structure and put them on a king plot, even if you calculate the center of mass, you get a relatively large deviation from linearity, I believe on the order of a megahertz. However, I would think that if one looks at things like anomalous hyperfine shift and hyperfine shift more accurately, it should be possible to add these to the graph. We would love to add them to the graph if we understand better and can somehow subtract this nonlinearity that they would add, because as I said, the most valuable thing that we can add to this is more isotopes, because it restricts our possibilities in a higher dimensional space. And so we will be looking in the future at measuring and analyzing what 171 and 173 do. If we could add them, we would have a lot more restrictions on what the possible effects could be.
David, I think you can speak now.
Yeah, one more question. On that Ramsey probe plot, there seemed to be more structure in it than at least I thought you pointed at.
Yes, you have a very you have a good eye. So basically what you have here is there are different on this plot is the most so in general when we do the Ramsey plots, it's complicated, but I'm not showing you the full spectrum because there are different magnetic sublevels, and then on each of the magnetic on the Zeeman transitions you have an additional effect from the motion frequencies of the ion that also appears as sidebands that are at the 1 megahertz level. So basically, the full plot has both motional frequencies of the ions and the Zeeman transitions. Here we try to separate them sufficiently to see whether there's additional structure on it. Maybe there is a little bit, I'm not sure. Were you referring to something particular in this graph? Or?
Well, I mean, just on that central one, there seems to be a lobe on the side, and then there's another one at the right, which seems to be split.
Yeah, I'm not sure. I have to look at this. How much of this is, is noise, and how much of this is, is real data. I think that at this level, we are not. Yeah, I have to look. I believe that this is just noise. I think that for this, I'm not sure now which spectrum I'm showing. We have, some preliminary spectra where we measured where the lines are particular in part overlapping, and then we have the final data that we analyzed.
More questions? Maybe I can briefly ask one. I was wondering about adding the neutral ytterbium. Would that add additional systematic effects? I mean, you suddenly have an electron more, right? So
it's really not, because you can think of the neutral atom just like, doing a transition from some other level to some other level.
I see.
Right? It's like as if you did, in the ion, from some other S state to some other D state or some other F state, right? It's just a new electron configuration, really. And you're just measuring frequency differences. I mean, even though we are measuring optical frequencies, right? We are measuring differences. So our baseline is the 2 gigahertz frequency difference. So know that I think it would not bring any new qualitative complications. The beauty of it is that basically because it has a different S state, right now the S state contribution to the sensitivity cancels, and we're only sensitive to FB. So we believe that it will give us more sensitivity in the interesting high mass region. Basically in this high mass region you have this cancellation, and if the S electrons are simply closer to the nucleus, and therefore we think that this line will have a different slope in this high mass region. It will not be as steep, the fall off in sensitivity.
Okay. Do we have more questions? Seems like not. We had a lot of good questions and good interaction.
Yeah, somebody immediately spotted the quadrupole shift.
Expert audience, yes. So, so I would say thanks again to Vladan for the great talk. It's really, really nice, really interesting. And I think we close out then. I guess Kobe closes out. Thank you.
Thank you very much for coming.
Thanks everyone for joining in.